I hope you guys can see my screen. Is it visible?
Yes, ma'am.
Okay. Yes, ma'am. So good afternoon all. Today we are going to discuss about the session 8, which is on Introductory Organic Chemistry second, which is an NPTEL course running on the NPTEL platform. So the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. And I am Simran, your PMRF teaching assistant. So this is the last session for this entire syllabus. So we are here to discuss the week 8 lecture that is about rearrangements. So anyone has any doubt regarding the previous lectures, please tell me so that I can take up your questions. Anyone has any doubts?
Ma'am,
Yes.
um, ma'am, can you explain again the Robinson
um, I can't hear you. Can you speak loudly?
annulation, ma'am?
Yeah, yeah. Okay, so you have a doubt on that.
Yeah, ma'am.
So what's the problem? I mean, where is the thing which you are not understanding?
Ma'am, basically, generally, I want to know about that, ma'am. What is the concept actually?
Okay. So basically, the concept there is to generate the alpha beta unsaturated cyclohexane rings, right? So the concept here was I have told you guys to do the aldol condensation first, and then the dehydration step takes place to generate that alpha beta unsaturated bond, right? So basically, it is a method to generate the alpha beta unsaturated ketones. Okay. So it is a name reaction for this for the purpose to generate the alpha beta unsaturated ketones by using an aldol condensation, and after that dehydration will take place, right? So that is the basic concept behind the rearrangement or the reaction. Have you understand?
Okay, ma'am. Thank you, ma'am.
Okay. Any other doubts? Okay. So shall I proceed with the week 8? Okay. So today's topic is rearrangements. So we have heard about this term rearrangements many times. Okay. So here we will discuss about some problems regarding the various rearrangement which we encounter in a daily basis. Okay. So this is the basic rearrangements which we are talking about today. So nothing very much hard. So we are starting with the problem one. So guys, they are asking the major product of the following reaction is. So as you can see, they are putting this particular ketone in presence of acid. Okay. So what here first happen will be like, first of all, this ketone. Guys, please join on time. Okay. So in the problem one, they are asking the major product of the reaction. Okay. So here they are treating this ketone in the presence of acid. So what can happen? First of all, this acid will protonate this particular oxygen of this carbonyl, right? And a positive charge will get generate here, which is a oxonium ion, which is going to generate, right? So first of all, this will happen for sure because we have an acid in our system, and which will protonate our oxygen of the carbonyl group. Okay. What will happen next then? See, this is a four-membered ring. As you can see, it is a very strained system. Agreed or not? Is four-membered ring strained or not? Anyone? Is this ring is strained or not? The four-membered ring, I'm asking.
Yes, madam. Four-member ring is strained.
Yeah, it is very much
According
strained.
to Bayes strain angle theory.
Very good. So the according to the Bayer strain theory, the four-membered ring is very much strained. So to release the strain. The driving force of these kind of reactions are to release the strain of this particular ring. So when this ring get cleaved, okay, so this is how it will get cleaved. So when this ring get cleaved, what it will generate, it will form a five-membered ring rather than the four-membered ring. Okay, so as we know that five-membered ring in turn is very much stable than the four-membered ring. Okay, so here the name reaction which is corresponding to that particular thing is the Merwin-Wagner rearrangement, which we are talking about today. Okay, so here what happens first is, when you take this ketone in presence of acid, first of all the protonation of this oxygen will takes place, and after that you have choice, rather this bond will get cleaved, this bond will get cleaved to give you a particular oxonium ion generation, and otherwise this bond will get cleaved. So which will prefer, either this bond will cleave or this bond, because it is the four membered ring which is very much strained in nature, and it wants to release this particular strain to get the five membered configuration, because this is a driving force of this reaction to take place. That is why this kind of bond get cleaved and this oxonium ion get neutralized like this. See here. So after the cleavage of this four-membered ring, this kind of intermediate get formed. This kind of intermediate, okay, and a positive charge on this carbon get generated, because here you are cleaving this bond to connect this kind of bond, but here one positive charges appear on this particular carbon, right? So what will happen next? See, there is a lone pair of electron which is present on oxygen. Okay, so after that, you have a choice uh, to either to cleave this bond, sorry, either to cleave this bond or this bond. So which will get cleaved? See, if you cleave this bond, now here this particular joint will take place. The CC bond formation will take place, but here you will find a carbocation at this position, at this position. Now there is no further stabilization of this carbocation, but here if you cleave the bond like this, here the carbocation which is forming on this particular carbon, right? So here there is a stabilization which is induced by the lone pair of electrons of this particular oxygen, giving this ketone moiety. So this is the particular product which you have basically appeared after the Merwin-Wagner rearrangement. So this is the particular product which you get. So this is how the Merwin-Wagner rearrangement proceeds. In the presence of acid, whenever you treat a ketone in presence of acid, what will happen? First, the protonation of this ketone takes place, and after that, if there is a ring strain in the adjacent particular ring present, then this kind of bond cleavage takes place to release the ring strain, that is the particular driving force of this reaction to takes place. And after the formation of this carbocation, the cleavage of this bond will induce a positive charge on this particular carbon, which is neutralized again by this lone pair of oxygen to give the ketone moiety. Is it understood or not, the mechanism? Anyone has any doubt regarding this?
Ma'am, I have a doubt after the intermediate formation. Ma'am.
Which intermediate? This intermediate
Third one,
formation?
ma'am. Next one.
Okay, next. Yeah, like this one. This intermediate. Okay, so here, see what will happen. I have told you guys about whenever we have an ketone, acids, or a carbonyl group present, functional groups in the system, and we treat it with acid. What will happen first is, first of all, this carbonyl oxygen will get protonate by the acid. Okay, and after that this oxonium ion generation will take place. So first this oxonium ion will generation will take place, and to neutralize this oxonium positive charge, this bond shifts, right? This bond cleaves, and here now if you consider this positive charge is generated on this particular carbon after the cleavage of this oxonium and carbonyl bond, then what happens to neutralize this positive charge? The four membered ring opens up to release the ring strain which it has, and now a five membered ring formation takes place, and this positive charge on this carbon get neutralized, right? But here, as you see, that this carbon is a tetravalent carbon, right? Four bonds, but one of the bond you are cleaving. Now a positive charge will get generated on this particular carbon, right? So here positive charge will get generated. So now either you have an option to cleave this bond, either you can cleave this bond to neutralize this positive charge, or you can cleave this bond to neutralize this positive charge. So which one you prefer? After the cleavage, you have to see the positive charge on which it is the carbon is getting, is it stabilized or not? You have to see the generation of positive charge, where it is getting generated, either it can be stabilized or not. So first of all, see here, if you cleave this bond, then a positive charge will appear here on this carbon, right? Because you are cleaving now this bond. So is there any group or functional group which is present to neutralize the positive charge or to stabilize the positive charge if you cleave this bond? Tell me.
No, ma'am.
Yeah, no. There is no groups that are present to neutralize this positive charge which is getting formed here. But here, when you cleave this bond, right, this CC bond, if you cleave it, then what will happen? This kind of bond is now getting formed, right? This bond is now getting formed. Now, this carbon will get a positive charge, right? So, after the formation of this positive charge, there is oxygen lone pairs which can now stabilize that positive charge to give particularly down this bond, and that is how it is stabilizing here. So a ketone is getting formed with two five membered rings. So here you started with a six membered ring and a four membered ring, but you ended up with a product with five membered ring both, right? With a five membered ring both. So now just tell me, that is the reactant more stabilized or the product is more stabilized based on the ring formation, the number of ring formation? Anyone? Just make a guess.
Product will
Yeah, product is very stabilized. Why? Because we have seen, according to the pair strain theory, that five membered ring in turn very stabilized, then six membered ring. So five membered rings are very much stabilized, then six, and after four, then three. So this kind of trend is going on, right? So in the reactant, you have that six membered ring which is stabilized, no doubt, but have a four membered strain ring, right? So to neutralize that ring strain, this kind of the driving force is only the ring strain which is having in the four membered ring, right? To neutralize the ring strain, the following rearrangement is taking place to get you a five and five membered ring formation. Okay, is it clear now, everyone?
yes, ma'am.
Yeah. So this is known as Wagner-Nervin rearrangement. Okay. So the driving force of these kind of rearrangements are the just releasing the ring state, okay, or the formation of more stable carbocation, you can say, okay. So the answer of this problem will be, which one is the answer? Option?
Option D, ma'am.
Yeah.
Fourth.
Yes. Option fourth will be the answer. Okay. So shall I proceed to problem two? Everyone understood the answer or not? Shall I proceed?
Yeah, ma'am. Yes, ma'am.
Okay. See, in the problem 2, they are asking what is the major rearrangement product of the following reaction. So now here also you have what? A six member ring with a four member ring fused with a four member ring. Okay. Here also the same condition is there, that is the acid condition. So what happened first is the protonation of this oxygen of the carbonyl group takes place. The oxonium ion generation will take place, and this further goes up, okay, to neutralize the positive charge which is getting on the oxygen. So now what will happen here is, see, the driving force, although here is also the ring strain which is having in the four membered ring, so it wants to get in a conformation which is more stable than the four membered ring, right? So here what will happen, there is a conjugation as you can see. So after conjugation, when it is getting protonate, when it is getting protonate, okay, this kind of scenario is there. So it is getting protonate, and after that, this conjugation takes place. So you will end up with having a positive charge as at particularly this carbon, right? Is it understood?
Yes, ma'am.
Yeah, this positive charge is getting generated on this particular carbon. Why? Because when you have an acid condition, the protonation takes place, and to neutralize this positive charge, what will happen when there is a conjugation, then this kind of conjugation takes place and a positive charge is getting generated at this carbon. So now what will happen next is that this ring can get open up, right? This is why this kind of rearrangement is there, because of the ring strains. So to neutralize this ring strain, what happen is this four membered ring wants to open up. So now it will get open up to form a what? How many membered ring it will form?
Five number ring.
Yeah.
Five.
So it will form a five membered ring. So this is how it is going. Like first of all, the protonation takes place. After that, this conjugation is taking place to neutralize the positive charge which is getting on the oxygen. After that, this ring strain is neutralized by formation of a five-membered ring. Now, if you are cleaving this bond, see, if you are cleaving this bond at this particular carbon, so now the next positive charge, that is the next carbocation which is getting generated, will be on this carbon, right? This particular carbon now will get a positive charge after the formation of five membered ring. So now what will happen, that you have successfully released the strain of a four membered ring, right? But now you have to stabilize this particular positive charge. So now there is a hydrogen which is present at this particular carbon, and you also can see that it can be a aromatized system, right? It can be a aromatized system if you just pull this proton and you get a benzene ring formation here. So, from a non-aromatized system, you are getting a aromatized system. So, you are getting a very stable system, because a non-aromatized fused with a four-membered ring, and you in the product you are getting what? A aromatized system with a fused with a five-membered ring. So now, which is more stable, the reactant or the product?
Again, the product.
Very good. Again, the product is more stabilized. Okay. So here, the name reaction is not the Meerwin Wenger, because where you was getting not a functionalized, not a aromatized system. You are not getting generated a aromatized system from a ketone functional group. You are getting a ketone functional group with a more stable system only. So here, the name reaction. Guys, can you please just mute your mic? Yeah, thank you. So from this non-aromatized system you are getting an aromatized system. So basically this rearrangement is known as diene phenol rearrangement, because here from this diene means that you have a double bond with an enon system, that is a carbonyl system. So you are getting a from a diene system you are getting a phenol system. So that is why this rearrangement is known as diene phenol rearrangement. Okay, so here the driving force is again the release of the string strain of four membered ring, but also here what you are getting generated is this di non-functionality is going to the phenol functionality. Okay, so that is why this rearrangement is called as di non-phenol rearrangement. Okay, so is it understood or not, the mechanism? Anyone has any doubt regarding this?
No, ma'am.
Madam, one doubt, madam.
Yeah.
Actually, this is the 100%. This product will form 100%.
Okay, so what are you expecting other than this?
Other than this, the four-member ring, this bond, either this bond or
Yeah.
this bond, will
So,
break, and
yeah.
it can lead to open chain also, no, madam. Open chain can release a pressure, the ring strain. Open chain can release the ring strain.
Okay, so you are telling that either this carbon bond or this carbon bond
Uh,
both can cleave,
yes, ma'am.
right?
Yes, ma'am.
This and this.
Yes, ma'am.
Okay, so just tell me that I am relating it like this bond is forming. So just tell me that if this bond get baked, so there is again a conjugation, right? If not on
Yes, ma'am.
this particular thing you are telling about this, see what happens here, that this bond is also get cleaved, and again due to
Yes,
the rearrangement this particular bond goes up. So what will you end up is this five member ring formation on this right hand side, either than the left hand side you are getting this on the right hand side, and the same things are getting formed. See, here also you will get this bond, okay, and OH functionality is there, right? And
yes, ma'am.
here this bond is retained. There is no change at this carbon. So this bond is retained, and
Yes,
this five membered ring is now getting formed on this side. Okay. So the
yes, ma'am.
carbocation which is present here is fixed on this particular carbon, because this is the carbon that is tetravalent and that is getting a positive charge after the cleavage. Okay. So just tell me
Okay.
that if it is the case, then here also you have the hydrogen. Just figure out this kind of bond, right? On the red, which I have drawn on the red, right? That is what
Yes, ma'am.
your functional groups are. So there is also a hydrogen bond, which is CH bond that is present. So again, this
Yes, ma'am.
proton can release, and you will end up getting a again a aromatized system. So now you will have again the same product but on the left hand side. Okay, this system is not there, but the left hand side you have a five member ring with a phenol again.
Yes,
So there
yes,
is
ma'am.
two possibilities which can be made it, but at the end you will end up with getting a same product. Okay, so this
Okay.
is the same product which you are getting on the left or the right. So two possibilities are there, but you will end up with only one possibility, because on the both the hand side, if you form the products are identical. Okay,
Yes, ma'am. Yes,
so that is why you will end up with getting 100% of this kind of product. Understood?
ma'am. Yes, ma'am. Thank you, ma'am.
Okay.
Thank you. Thank you.
Okay. So any other doubts regarding this problem? Okay. So just tell me the answer then. Which is the correct option?
Option A, ma'am.
Very good. Option A will be the
Correct.
correct one. Okay. So I'm proceeding to problem 3. I hope you guys understood the both the problems. Any doubt, just tell me, okay? So in the problem 3, they are asking the given reaction leads to the formation of what? So there are four options, and amongst which you have to select which is the correct one. So here what happens is the reaction which is going to give you the lead formation is, first of all, this ketone is treated under the hydrogen peroxide condition in acetic acid. So hydrogen peroxide, as you know, is an oxidizing agent, right? So what will happen now? It is the most oxidized product. Can it be oxidized further? This ketone, if you treat this particular hydrogen peroxide as an oxidizing agent only, can this ketone further be oxidized to any functionality? No, right? Because it is the most oxidized system. Because ketone cannot be further oxidized, right? So here it is not just acting as an oxidizing agent. What it will do then, just see this particular mechanism, what will happen? See, the lone pair of oxygens are present on this H2O2 system, that is a hydrogen peroxide system. So what will happen, that instead of acting as an oxidizing agent, it will do the nucleophilic addition, because the system itself is very much now oxidized. You cannot further oxidize it to any system, right? Because ketone cannot be further oxidized. It is not the alcohol, it is not the aldehyde, it is not further functionality, right? So here, the nucleophilic addition takes place. What will happen? This lone pair of electrons on oxygen will attack on the carbonyl carbon, and you will end up with this tetrahedral intermediate. Okay. After that, there is a proton transfer here. You have that proton, and this proton will get cleaved. Now, there is a proton transfer on this OH. This particular negative charge will take up this proton, and here, this kind of system is getting formed. Okay. Now, what will happen next is this water or acetic acid, what you can say here, what will happen in this case? First of all, this oxygen will attack on this particular carbonyl carbon, leading to the formation of O minus. Now, this O minus will abstract a proton from this, and this positive charge get neutralized. So after that, this the neutralization of the positive charge, what will happen next is this OH bond is there and this kind of bond is there. So now what will happen, that this after the formation of this, there is a possibility either this four membered ring CC bond get cleaved, or this bond get this bond get cleaved. Okay. So both of which can cleave, and regarding that, the same product will get formed. In the previous case, we have seen, right, because as it is containing the same carbon, that is the tetravalent carbon, the cleavage of both A and B will lead you the same product. So what happens here is, first of all, this particular carbon carbon bond is getting cleaved because of the ring strain, which is four membered ring having. Okay, so now it will abstract an oxygen from this position, and this OH will leave out. Now you have, I am just skipping a particular intermediate in between. What will happen here is, when you get this formation of five membered ring here, then you will end up having this positive charge on this carbon, right or not? Right? Because you have this carbon carbon bond which is now getting cleaved to get you this five membered ring with oxygen. Now this positive charge is there. Now you have an OH from there. So now this particular bond get cleaved, and this this carbon positive charge is now getting neutralized by this OH bond. So this kind of system is now getting generated, of particularly lactone ring is getting generated here. Okay. So I am repeating the particular mechanism again because I know it is a bit tricky to understand. See, what will happen first is, you have that H2O2 in the system, okay? That is the oxidizing agent, that is the hydrogen peroxide. But now you can see here that because this is the like very much oxidized system, that is why this hydrogen peroxide is now not acting as an oxidizing agent alone. It is now behaving as a nucleophile, because oxygen has a lone pair of electrons, and you know that carbonyl carbon is very much electrophilic in nature. So this oxygen then attack on this carbonyl carbon, and this oxonium ion formation takes place. Okay. So this O minus will abstract the proton from this H2O2, that is the hydrogen peroxide, and after the abstraction of proton, this OH is getting formed. Now the next step is, if there is OH O bond which is here, see, if there is this kind of bond, then what will happen, that either you have this CC bond to be cleaved because of the ring strain, or this bond to be cleaved. So you will end up with the same product, either this bond cleaved, either this bond cleaved. So what will happen, that this bond cleavage takes place, as it is more electron density is there. So this O is now trapped, and this OH minus will leave out. So now this positive charge is getting generated on this carbon of the four membered ring, which is now five membered ring. Okay. So this is now stabilized by this OH group, and a ketone is getting formed, that is a lactone ring is getting formed out there. So this is how you will end up with having a lactone ring which is 5 membered rather than the 4 membered ketone in this reactant. Okay. So is it understood the mechanism? Anyone has any doubt? Is it clear or it's not?
Madam, excuse me, madam. Excuse me, madam.
Yeah.
You are saying you told this electron density regarding this bond
Hmm.
compared to this bond.
Yeah.
Please tell me once again. Please
Okay.
repeat
Oh,
me.
okay. Okay. See, what I am referring is that this particular carbon is there. Okay. You have a bond between this and this carbon, right? And here, what you have is a secondary carbon, and this is a tertiary carbon which is present here, right?
Yes,
So see, if you keep this bond, there is a tertiary carbon, and you have seen the migratory aptitude. You have learned about that migratory aptitude of the
yes, ma'am.
carbons, right? So where the electron density is more, the migratory aptitude is high, right? So here at one side you have the tertiary carbon, and at the second side you have the secondary carbon. So which migratory aptitude is high? The tertiary carbon has a higher migratory aptitude than the secondary carbon. That is why I'm telling here that this particular bond cleavage taking place, and this tertiary carbon is now getting migrated to, because of the this bond you are getting generated this CO bond with this tertiary carbon rather than this secondary carbon. Is it understood now?
Yes, ma'am. Yes, ma'am. Clear. Thank you, ma'am.
Okay.
Thank you. Thank you.
Okay. Other questions regarding the mechanism? Anyone? Okay. If no one has any questions, then tell me which is the correct option right here.
Second option C.
Yeah.
Yes.
Second one
Third.
is the,
Second one.
yeah, it is the correct option. Okay.
Lactose.
Okay, so I'm proceeding to problem 4. I hope all guys, you have understood the mechanism. If not, just tell me. Okay. So in the problem 4, they are telling that identify the major rearrangement product formed in the given reaction. So they are telling that this is a rearrangement, and you have to identify the major product. So what they are treating here is they are treating this particular carboxylate ring with this Lewis acid, that is the aluminum trichloride, okay, at 90 degrees centigrade. So what happens here is, see, this is the name reaction which refers to the Fry's rearrangement, okay. So here you will end up with having two products, but here they are asking that which is the major product. So now let us have a look. See, this is the Lewis acid, as you know, aluminum trichloride. So what will happen here is this oxygen, as I have told you previously many times, that the carbonyl group, in the carbonyl group, the carbonyl carbon is electrophilic but the oxygen is nucleophilic. That is why the acid is getting binded towards this oxygen. So in the previous case we have also seen that this ice acid is attacking on this particular carbonyl oxygen, okay. So same with this case, AlCl3 is also in Lewis acid. That is why it is chelating with this, protonating basically this particular oxygen to form this oxonium ion. Okay, so the lone pair gives to the aluminium, and after that there is a negative charge which is getting generated on aluminium, and a positive charge which is getting generated on the oxygen. That is the oxonium ion formation. So now what will happen, that this particular O, that is the phenoxide, is now attaching towards this aluminium and giving this oxonium ion back, because anyone has to stabilize this O positive, which is very unstable, right? A positive charge on an electronegative atom is very unstable, so that is why we have to stabilize it. So how it will happen? that this CO bond, that this is carboxylate, that is getting cleaved. So now here this CO bond is now getting cleaved, and takes up this aluminium, and this positive charge is now getting neutralized. So this kind of intermediate you are getting. You are getting what? This kind of intermediate. That this is a carbonyl, and you are getting this R with the positive charge here. Positive charge at this carbon. Right? So this is the acetyl which you are getting. So now what will happen, as you can see that here you have two possibilities. In the phenol also you can see that you can end up with a ortho and para products, right? Because of the conjugation. So now here also you have this kind of conjugation. Either this ortho for product formation will take place, or the meta product formation will take place. Why? Because here also the same concept takes place of the electrophilic addition, that this ortho and para electron density is higher due to the resonance effect here, and that is why you will have both the products, this ortho substituted phenols as well as you get the para substituted phenols. This is the simple electrophilic substitution addition reactions. Sorry, substitution. Electrophilic addition reaction, right? So, which you have seen previously. So now, what will happen in the first case? First of all, if you have this Lewis acid, it will bind towards this oxonium ion generation, and after that, this to stabilize this positive charge which is getting generated on the oxygen, what will happen? This carboxylate CO bond is getting cleaved, and now it will attack towards the aluminium, and this oxonium ion is now getting neutralized. So now this kind of intermediate is getting formed. So here you can say that this aluminum is minus. Now there is a conjugation which is present between this resonance between this phenyl ring and this O. So now there is a ortho and para product which is getting in the system. Why? Because resonance stabilization is there, and due to the resonance there is a higher electron density which is present on the ortho and para position rather than the meta. That is why, which is the key concept with the phenols, with the electron donating groups you guys are having, right? So here you will end up with having two product, either the meta substituted or either the para substituted. Just tell me, this much is clear to all of you, or I have to repeat? Then we will see that which one is major or which one is minor. Just tell me that the two product formation, is it clear, this rearrangement, this price rearrangement?
Excuse me, madam.
Yeah.
Mainly ortho para position electron density more,
Yeah.
and because of that it attacks acylium category.
Yeah.
Even-
Yes.
Thank you, ma'am.
Okay.
Thank you.
Any other doubts? I'm asking everyone. Anyone has any doubt regarding this
No, ma'am.
comparison? Okay. So if you guys don't have any doubt, just see what happens here is this psyllium cation is getting trapped, and you get the ortho as well as para product formation. Okay. So now there is a temperature dependence which is written on this particular arrows. So here the condition is that 90 degree centigrade is the condition. So now just tell me, is 90 degree that much high? Like 370 Kelvin, they are telling that 370 Kelvin. Greater than that, we are getting this ortho product, right? So in this temperature condition, which product will which product will dominate, the ortho or the para product? Any guesses?
Para, madam. Para, madam. Para.
Para. Any other one? Anyone saying ortho?
Ortho, ma'am.
Okay. Any other suggestions? For someone saying both are dominate. Okay. See, what happens there is that at the room temperature they are showing that you are getting this particular para product formation, and at a very high temperature only you are getting that ortho product. Why that high temperature is needed? Because see, what happens there is there is a hydrogen bonding which is present in this ortho product, right? There is a hydrogen bonding. This hydrogen is getting the hydrogen in the hydrogen bond formation with this carbonyl oxygen, right? But here there is a intermolecular hydrogen bonding which is present in this system, and in this system there is a intramolecular hydrogen bonding which is present, right or wrong?
And excuse me, how you are saying intramolecular? Intramolecular.
See, how I'm saying intramolecular is there is a ketone moiety which is functionality that is present here. If you write this as like this, see, if you write this OH as this, then just tell me that is there is any bonding which is present between this oxygen and hydrogen. This is what, this is a
Yes, yes,
hydrogen,
yes, ma'am. Yes,
this
ma'am.
is a hydrogen bond, right? So
Yes, ma'am.
that
Yes,
is
ma'am.
why
Thank you.
telling that there is a six membered intermediate formation due to the hydrogen bonding formation, and also it is present in the same molecule, the hydrogen donating species and the hydrogen acceptor, both are present in the same molecule. That is why we are referring that it is a intramolecular hydrogen bond, right? And here, if you can see that there this OH is very far away from this acyl group to show the hydrogen bond. Yes. So what happens here is you need another molecule of this to show up that hydrogen bonding. So that is why I'm telling that it is a intermolecular. That is two molecules needed for this hydrogen bond formation, right? But here you need only one molecule to show that hydrogen bond formation. So it is a intramolecular hydrogen bonding, and in this case para position you have intermolecular hydrogen bonding. Is it clear, the inter intra? Any questions? Have you guys understood what is intermolecular, what is intramolecular? Okay, so it seems like you guys have understood. So this is how intermolecular and intramolecular hydrogen bonding takes place. So see, so this is more stable product intramolecular than the intermolecular product, right? So this ortho product is more stable. So that is why at high temperature, the thermodynamically more stable product formation takes place. So at high temperature, you will end up having this ortho bond formation rather than this para product. Okay. So for the formation of the ortho product, you need high temperature to be maintained, because at high temperature only the thermodynamically stable product gets formed. At low temperature, the kinetically stable product get formed. Okay. So at room temperature, sorry,
Excuse me, ma'am. May I ask something?
sorry,
Ma'am, may I ask a question?
yeah, sure.
Ma'am, but we have seen in case of ortho and paranitrophenol that like orthonitrophenol is less volatile.
Hmm.
So एक higher. So I think that मुझे ऐसा लगता है कि I think para will be formed at higher temperature.
Okay, para will be forming at high temperature.
I think so.
Okay, okay. See, I will tell you according to your example only. Okay, so that orthonitrophenol. Okay, just tell me that orthonitrophenol. There is the intramolecular hydrogen bonding in the ortho case. Okay,
Yes, ma'am.
yeah. So intramolecular hydrogen bonding is there in the ortho case, and in the paranitrophenol case, there is intermolecular hydrogen bonding which is present.
Yes, ma'am.
Okay. So tell me, according to your opinion, the intramolecular hydrogen bonding is more stable or the intermolecular hydrogen bonding is more stable?
Ma'am, intermolecular.
Inter.
Yes, ma'am.
Okay. Okay. So if you are saying that intermolecular hydrogen bond formation is more stable, then tell me that in the NMR, in the everything, if you dilute the things, okay, if you have this para nitrophenol in the system, just let let us take as an example that you have orthonitrophenol in the system. Okay, and you are diluting it. You are diluting your sample of orthonitrophenol with water or with anything. Okay, you are diluting
Hmm.
this, so a dilution takes place. So now your uh, the molecule of paranitrophenol, which is showing the intermolecular hydrogen bonding, which is dependent on the concentration. See, intermolecular hydrogen bonding is very much dependent on concentration, because if you get the diluted one now, that what happens here is the molecules, the two molecules go far away from each other. So now there is no intermolecular hydrogen bonding which they are showing up. So that is why it is dependent on dilution. It is depending on very much on other factors. But here in the intramolecular case, what happens if you have intramolecularly arranged system in the hand, that is the ortho nitrophenol, if in say in the sample, then after diluting also the intramolecular hydrogen bonding doesn't break. Understanding this, say your molecule how far they will go in the solution for the orthonitrophenol, but there is intramolecular hydrogen bonding which is present, because it is not dependent on the two molecule. It is the single molecule which is showing up your intramolecular hydrogen bonding. So after dilution also it is going to give you the intramolecular hydrogen bonding. But in the case of paranitrophenol, that after diluting the system, you will end up with having no intermolecular hydrogen bonding. So intermolecular hydrogen bonding is very, I'm not saying very less stable, it is less stable, or it is less convenient than the intramolecular hydrogen bonding, because it is depending on very much on the conditions like dilution, temperature, anything else. Okay, so that is why you can't say that intramolecular hydrogen bonding is weak than intermolecular hydrogen bonding. Rather, you can say that intramolecular hydrogen bonding is strong than intermolecular hydrogen bonding. This concept, is it clear that why intermolecular hydrogen bonding is strong than intra? Sorry, why intra is strong than inter? Is it clear?
Yes, ma'am.
Yeah. So that is why you are saying that it is volatile. See, in the case of orthonitrophenol, it is less volatile than paranitrophenol. Why? Because intramolecular hydrogen bonding is strong than intermolecular hydrogen bonding. You get a clear cut distinction from the volatility, from the boiling point. Okay. So here the same concept is there. Here this ortho product is much much stabilized, because intermolecular hydrogen bonding is very much stabilized than the intermolecular. That is why on the high temperature it is not volatile. It is not getting absorbed up. So you are getting this product at high temperature rather than the lower temperature. That ortho product. Is this much clear, or I have to repeat anything else? You have any doubt?
No, ma'am.
Okay. So here, based on the consideration, just tell me which is the more stable product, this ortho product or the para product?
Ortho, madam.
Ortho.
Ortho is more stable.
Yeah, ortho is more stable. So that is why you need high temperature to form this ortho product and low temperature to form this para product. See, when you are asking about the major product, you have to see that aspects. If you are saying that just tell me the product of the reaction, this reaction, just tell me the product, then you will write both the products, the ortho product, the para product. But if you are asking about the major and minor, then this temperature aspect come into your mind. Okay, that why this temperature is necessary. So here in the question they are asking that 90 degrees is the temperature which they have maintained. So 90 degrees is not that much high temperature. Okay, so that is why this para product is dominate rather than this ortho product. So for the ortho product formation, you need high temperature to be maintained. Is it clear or not?
Yes, ma'am.
Okay. So now just tell me the answer if it is clear. Which one is the major product in this case?
Para, madam. Para isomer.
Yeah, the para product is the major one. Okay. Anyone has any doubt regarding this problem? Any doubt?
Excuse me, madam.
Yeah.
If we do the reaction under light condition, what will be the scenario, the
And
result?
under light condition, I didn't understand the light condition.
Photochemical.
Okay, okay. Under photochemical condition. See, photochemical pathway doesn't go like this positive negative substituents. They goes by radical formation. So the scenario is although another level. So you can't imagine that this product is major or this product is minor. So you have to put in the flask and you have to see that which product is now getting. Okay. So there is an anionic mechanism which is following this Fry's rearrangement, right? But when you go for the photochemical, you have that radical formations. So radical formation is another concept. So here you can't say which is the major or minor unless you have a proof. So you have to keep in the round bottom class the things and you have to add the things and then you have to see what will happen. I can surely say that this is not the mechanism which is going to uh, happen in the photochemical condition. Okay. So here it is an ionic and the photochemical you will end up with having the radical formation. Okay.
Yes. Thank you. Thank
Okay.
you. Very good.
So coming to the problem 5, so they are asking to predict the major product formation in the following rearrangement. So if you remember, I have talked about this rearrangement previously. That is the benzylic acid rearrangement. Okay. So what happens here is whenever you have 1,2-diketone in the system and you treating it in the basic condition, so the uh, reaction which is going to take place is the benzylic acid rearrangement. Okay. So what happens here is this base is present. So is there any acidic proton which it will abstract? I mean, have an acidic proton, no doubt. It will abstract that. But what will be the fate? Nothing happens after that. So here, this NaOH or OH, KOH, whatever it is acting as an nucleophile. So first of all, it will attack one of the carbonyl and this goes up. Right? What happened then? This kind of product is getting formed. This tetrahedral intermediate is there. Okay. So now if I have to ask you that which of the things will migrate, this phenol will migrate or this OH will migrate? Migratory aptitude of this phenol and this hydroxyl, which is higher? See, there is a table of the migratory aptitudes. Because of the electron density, the things migrates. Okay. So if you have an electron withdrawing group which is attached to the system, then it will migrate less. If you have electron donating system which is present, it will migrate higher affinity. That is like tertiary carbon is migrating higher aptitude with the secondary rather than primary. Okay. So here also the same scenario is there. Whenever you have this kind of base, then it will attack on this carbonyl carbon. This O minus will getting formed. When this O minus comes down, there is a particular competition between this pH, this phenyl ring, and this OH, which is to be migrated. So here this phenyl ring will migrate first to this, and this O minus again get generated with this acid at the end. Okay. So now you have what? You have an like proton in the system. So where this proton will come from? A base only. This protonation will takes place, proton transfer from this water takes place, and after that you will end up having this kind of product which is a benzylic acid. So here you will have this reactant which is known as benzyl, and in the product you will have this benzylic acid. So that is why it is known as benzylic acid rearrangement. Okay. So first of all, what will happen here in the basic condition, as it can act as a nucleophile. So first this carbonyl carbon is getting attacked by this base. After that, this O minus is getting generated, and after that, this phenyl ring is now migrating towards the adjacent carbon, and this acid is now getting formed here. This protonation takes place, and after that, this benzylic acid is getting formed. Is it clear the mechanism?
Ma'am, there are two benzene ring. The benzene ring which is having amino group having more electron releasing,
Huh.
more electron releasing.
Hmm.
So that will migrate, no madam?
Okay. See, you have to follow the basic concept here also. Just tell me that if there is the electron releasing group which is present in this ring, okay, so because of the delocalization now, it will give the electron density towards this phenyl ring, right? So here, which makes this carbon less electrophilic in nature. So why base will attack on that ring first? Base will attack on that ring, that carbonyl group, which is more electrophilic in nature. You have to keep this in mind in first place, that base will attack on the carbonyl carbon which is more electrophilic. So that is why it is going up here, not there. If it goes here, then you can say that yes, this O minus will get formed, and this phenyl or this aniline ring can also move. Like this aniline ring can also migrate. But if this will happen, if the base will attack this carbonyl carbon first. So why it is attacking on this carbonyl carbon first? Why not? Because here this amine is present, which is the electron donating group. Now this will donate the electron to this phenyl ring, and actually there's this carbon is not that much electrophilic like this carbon. So that is why base was first attacking on this, and that is why the migration of this ring is taking place rather than this aniline ring. Is it clear or not?
Yes, madam. Yes, madam. Thank you, ma'am.
Okay.
Thank you so much. Thank you so much.
So just tell me the answer then, if you understood the problem, which is the correct one.
B, second one.
No, 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 the second one. The first one will be the correct one, right?
Yes, yes.
Yeah. So
First
this
problem.
is the correct answer. So I'm proceeding to problem 6. So they are asking found like the major rearrangement product of this following reaction. So again, this is the standard example of Wagner-Meerwin rearrangement. See what will happen here. So the protonation can takes place. Either this hydroxyl get protonate, either this hydroxyl will get protonate. Both the possibilities are there. So after the protonation, what will happen? This water leave out, right? After the protonation. After protonation, if I will say that this is getting protonated, then what will happen? This water falls out. So a carbocation is getting generated here. So this five-membered ring can cleave and goes to stabilize this carbocation to form this six-membered ring. So now this positive charge is stabilized by this hydroxyl group which is present. So this kind of product is now getting formed. See, it is a very simple mechanistic problem. So anyone has any doubt in this? See, if you say that ma'am, this hydroxyl can also get protonate first, and this carbocation is also getting can get generated, right? This is the major thing which you guys are thinking. So here also, if this carbocation is getting formed, then this particular cc bond is getting cleaved, right? So here you have that OH which is present. If you are cleaving this bond, and if you are saying that this hydro OH can also goes down, then what happens? This positive charge is there, it can stabilize by this OH group, the lone pairs of this oxygen, and you will again end up with having same product. So either you will abstract the proton, you will add proton and abstract water from this side, or either you can abstract from this side, you will end up with having same product both the times. Okay, so is it clear the mechanism? Anyone has any doubt?
Madam,
Guys,
the second step,
yeah.
second to third step. This you can one more time. Please, madam, please.
Okay. See, I'm explaining the whole mechanism again. See, what happens if you have the acidic condition in the hand? what will happen? This oxygen has the lone pair of electron, it will take up the proton, right? And this H2O positive will get generated, right? And after that, this water is getting generated, and you can say that this water can leave out very easily. It is a good, because as a neutral species it is leaving out, right? So it will leave out very easily, and a carbocation is now getting generated at this carbon. So now what will happen, that here you have this cyclopentane ring. Then what will happen, that this CC bond, either it can cleave from this side, either it can cleave from this side. So if it is cleaving from this side, see, this side, which having this particular OH, if it is cleaving from this side, then this kind of six membered ring intermediate is getting formed. This is the fusion which is getting formed, because here you are getting this carbon bond formation, this and this carbon bond formation. So this six membered ring is formed, and after that you will having a carbon positive charge which is getting generated at this carbon, because now you have just shifted from five membered ring to six membered ring. So this carbon is having a positive charge. So this is neutralized by the OH lone pairs. So this is how you will end up with having a ketone in it. Is it clear now?
Yes, ma'am. Yes, ma'am.
Okay.
Thank you, ma'am. Thank you so much.
Okay. Okay. So if it is clear, just tell me the answer. Which is the correct option?
Option B, ma'am.
Option.
Option B, or, sorry, option C.
Yeah,
Option C,
option
ma'am.
C. Right. Option C will. So option B will be the.
Option B.
Option B will be the correct
Option D.
option,
You asked.
right? Okay. Everyone agreed?
B will be, yes.
Okay. So I'm going to problem 7, if it is understood. See, what they are asking, the final product in the reaction. So if you have any acid and you treat it with this hydrazoic acid, what will happen? It is a name reaction that is called as Schmidt rearrangement. Okay. So what will happen here is, first of all, if you have this hydrazoic acid in system, what will happen, that this acid protonates your this particular oxonium ion formation will take place, right? Either you can say that this OH is getting protonated, whatever you want you can write. So if this protonation, you will write that this protonation is taking place because of the acid, then what will happen, that this OH then comes up and this goes up, and you will end up having this kind of intermediate every time. Okay. After the removal of water, you will have this acyl cation, and you have that HN3 in the system. So you will write it as like HN double bond N double bond N. That is, this sign is electrophilic in nature and this sign is nucleophilic in nature. So now you need an nucleophile to trap this acyl cation. So what will happen, that after conjugation, you will like this CN bond will get formed, and this N2 is now leaving. How it will leave? That there is a isocyanide formation which is taking place. This R will goes here, and this double bond is getting formed by with this carbon and nitrogen, and N2 gets leave out. So after the removal of N2, this isocyanide intermediate is getting formed. So in the presence of water, what will happen, that this carbon, as you know, is the electrophilic in nature. So this water will attack this carbon, forming this type of intermediate, and this N positive is there. So after that, this oxonium ions, this OH and this O minus, will now gives out you CO2, and this primary amine is now getting formed. So all the way from this acid, from this hydrazoic, adding this hydrazoic acid, what you can generate? An acid amine from an acid you can generate. After you treat this acid in the presence of hydrazoic acid, you will take up the acid to amine. So you will have an amine with a carbon less. Just take this in mind, that you will end up having an amine with a carbon less, because here there is a carbon in carbon, which goes out as a CO2, and you will end up with this primary amine. So this is how, first of all, I will repeat this mechanism again because it is bit tricky to understand. So what will happen here, first of all, this, in the acid condition, this protonation takes place, and after that, this trapping will take place, right? After the conjugation, this OH minus will get formed. So after the removal of H2O, there is a positive charge that is creating on this particular carbon, and this acyl cation is getting formed. So now here comes the role of HN3 which you have added. So now this N will attack on the carbonyl carbon, and this kind of intermediate is getting generated. So now this R group, which is connected to carbon, it migrates towards nitrogen, and this bond then migrates here to give you a double bond. So now this N2 leaves out, and you will end up having an isocyanate intermediate. So in Schmidt rearrangement, in Lawson rearrangement, in Curtius rearrangement, in three of the rearrangement, you have the isocyanate intermediate which is getting generated in the reaction. So after that, this water is trapped by this carbon. Why? Because it is electrophilic in nature. So now this removal of CO2 will give you the primary amine formation. So from the acid, you have an amine formation. Okay. Is it clear the mechanism? Just go through it very quickly.
Madam, excuse me, madam.
Yeah.
Here, migration of alkyl group is important.
Yes.
Migration of alkyl group.
Yes.
Okay.
Because of the
It,
yeah. See,
tell me, madam, please.
yeah, yeah.
It will migrate along with the bond electron, madam.
Yes, it will migrate with the bond electrons. See, what happens here is you have that Cr bond, right? So here,
Yes, ma'am.
what will happen, because N2 wants to leave, because N2 can leave out, it is a gas. So here, a double bond formation takes place, and you have a nitrogen which is now getting in double bond formation. So this R group is now migrating from this carbon to nitrogen to give you a isocyanate intermediate which is stable. Okay, so the driving force is here to formation of the isocyanate intermediate. So which is the R bond, which is the R bond, the alkyl, aromatic, whatever it is, it migrates towards the nitrogen to generate a isocyanate intermediate, which is again trapped by the water. Okay, so
Yes,
the
ma'am.
driving force although is the generation of isocyanate intermediate. So whenever you have an acid, you treat it with hydrozoic acid, you will end up having an amine with a carbon less. Okay, just take this in the mind. So what will be the product in the case? In this case, we have the R as phenyl group. So what will be the product?
Aniline, madam. Aniline.
Yeah, aniline will be the form product. So first is the correct answer. Okay. Anyone has any doubt regarding the mechanism? Okay, so if no one has any doubt, I'm proceeding to last problem of this session, that is problem 8. Very quickly we go through this question. See, what they are asking here is, I have not mentioned the options. It's just for your information that this kind of rearrangement is there. Okay, so here they are asking, write the major product of the reaction. So this is the like alpha halo ketone, and if you treat it with a basic condition, what will happen? You have to figure it out. See, this base have the OH minus configuration. So what will happen, that this base either can act as a nucleophile, either can act as a base. So if you say that it is acting as a base, you must have an acidic proton in the system. So this proton is acidic. Base will first act as a base, and if there is no proton, acidic proton present in the system, only then it will act as a nucleophile. I have told you in many times previously also. We have seen the examples where we have base, but Here also we didn't have any acidic proton to leave out to give something. That is why it is behaving as a nucleophile. Okay. So here, if you treat it with the NaOH, it will act as a base first. It will abstract the proton which is acidic. So here, two set of protons are there, this and this. So which is more acidic? You have to figure it out. See, these protons are much more acidic. Why? Because after the formation of a carbon ion, it is getting it is getting in the conjugation to form the enolate. Here also enolate formation takes place, but it is not as much acidic as this. Okay, so here it first particularly abstract the proton from the beta position of this ketone, and what will happen? A carbon ion generation is taking place. After that, as Cl is a leaving group, it is a very good leaving group. We know. So here what happens that this O minus will enolize with this proton. But next, what will happen next? It comes down and this carbon ion then attack on this carbon to leave out this particular Cl to form this intermediate. To form this intermediate. There is a three-membered ring formation which is taking place. So this kind of intermediate is formed. Now again, the base have to now act as a nucleophile. So base is acting as a base, and it will take up the acidic proton only when the acidic proton is present in the system. Okay. So base will first act as base. Secondly, it will act as a nucleophile only if there is no proton, that is, there is no acidic proton present in the system. So here NaOH first acts as a base and it takes up the acidic proton to form the carbon ion, which then attack on the Cl containing carbon, which then leaves out, and this kind of cyclopropane ring is getting formed. Now it will act as a nucleophile. So after acting as a nucleophile, what happens that this kind of intermediate tetrahedral intermediate is getting generated. Now you have a choice. After coming back this O minus, there is a choice. Either the cyclopropane ring opens up on this side, either the cyclopropane ring opens up on this side. Okay. So if the cyclopropane ring opens up on this side, O minus ring, O minus carbon ion is getting generated at this carbon, and other carbon ion is getting generated at this carbon. So if it takes up the water, it takes up the proton from the water which is like cleaved from in the first step. It is getting dissociated, right? So here also it will take up the proton and will give you this. So just tell me that if this side cleavage takes place, then also you will have nothing substituted at these positions. So you will have the same product, either the cyclopropane ring opens up on this side or on this side. You have the same product. Okay. So here you will end up having this cyclopentane ring with an acid group. So this rearrangement is known as Favorsky rearrangement. Whenever you have this alpha haloketones in the system, what happens that base will first abstract the acidic proton, and after the formation of carbon ion, it will attack on the carbon containing the leaving group, and which leaves out to form this cyclopropane ring. Now the base will act as a nucleophile, and you have two options, right? Whether to open this up, whether to open this up. If you have any group that is stabilizing this carbon ion, then you will end up having that CC bond cleavage. Okay, here there is no competition because there is no substitution which is present on this cyclopentane ring. That is why opening on this side and this side will lead you the same product. So this is how this product formation will takes place. So is it clear the mechanism? Any doubts?
Madam, the cleavage of cyclopropane ring, either side, it will give the same product.
Yeah.
It will give the same. Thank you.
Yeah, because there is no substitution, right? If you have any substituted cyclopentane ring, then you see if here there is a electron withdrawing group which is present. Okay, or here if there is a electron withdrawing group which is present, then this carbon ion is getting stabilized by this electron withdrawing group. Now you have an majority of the formation of this kind of product. You have additional benefit to cleave this bond rather than the this bond. So that is why when substitutions are there, you have to look which is the most stable carbon and which is getting formed. Only that bond will get cleaved. Okay, but here as there is no competition, so both can cleave equally, but the product, as you know, is now identical in both the case. Okay.
Thank you, ma'am. Thank you.
Okay. So this is how you will end up with the cyclopentane ring and this product. Okay. So this is known as the Favorsky rearrangement. So this is it for today, and this is the last class, as I have told earlier that this is the last class for this session. So I'm not going to take up any further classes, and this is it for this particular course. So I hope you guys have enjoyed all the lectures. I hope you guys have attended all the lectures. You have seen all the lectures. If not, then my videos are available on the YouTube. You can go through many a times as much as you can, and the comment section is also open, so you can comment and you can ask the problems on that platform. I will answer you happily. And thank you so much for being in the class. Thank you so much for being attentive, for being response, and thank you so much for the patient listening. So we will
Thank
end
you.
up this class. Okay.
Thank you.
Thank you.
Okay.
Ma'am, the previous YouTube, that YouTube link, madam, YouTube link.
YouTube link. Okay. So I actually have to. You can type actually. This is a channel you can see that is named as Simran NPTEL-TA. So there is a channel with this name. You can find it. Okay.
Tell me,
So
madam, Simran.
yeah, I'm just typing in the chat box. Just have a look on that. Okay. So this is the name. This is the name I have just mentioned in the chat box. You guys can go through that channel, and there are videos which is available, and you can see that. Okay. Any problem you guys are facing, just tell me in the comment section. I will happy to answer you. Okay.
It is capital, yes, madam.
Yes.
Simran, capital, yes.
Yeah, it is capital. Okay.
Thank you, ma'am. Thank you, ma'am. Very kind of you.
Okay. Thank you so
Thank you.
much for attending the classes. Okay. So bye, all of you.